I'd like to thank the organizers for inviting me and giving me a chance to speak here. I've been in Germany many times, but not to this conference. I have never attended to this conference. This is the first time for me. And my aim today is to give a kind of survey on quaternion hermitian lattices and its application to supersingular abelian varieties. And I know nothing about cryptography, so I don't know if such things is useful for cryptography or not, but at least it is an interesting theory, so I'd like to give some survey. So I'd like to start from some very easy application. So I'd like to persuade you that the arithmetic theory is very useful. So let's start from supersingularity curve of algebraically closed field. And of course, you know that this endomorphism of E is maximal order over quaternion algebra, which is a division locally at P and infinity and split at all other primes. And we say that A is supersingular if A is isogenous to E to the n. Now there are a lot of interesting theories when n is 1, but when n is bigger or equal to 2, then the story is slightly different in a sense, so that it has different features. For example, class number of MND is 1. Here, MND is n by n ring matrices over D. And the class number is class number 1 means that all the left M and O ideal are principal. So this is obtained by strong approximation theorem, and this is very general theorem due to Kuneza and other people. And we can use this to for the application to the abelian supersingular abelian varieties. So there are two easy things. So the first one is any product of supersingularity curve are all automorphic when n is bigger than or equal to 2. So this is due to Shioda and Durini and August. And so there are finitely many different supersingularity curves when n is 1. But when n is bigger than or equal to 2, there is only one product of supersingularity curves. And this is called superspecial. And this is the first application. And maybe this is popular, and many people knows about this. But the second one is maybe not so popular. So through the minimal isogeny from phi to A, so the A is isogenous to n, so that there's some isogeny from E to the n to A. Then through this isogeny, when phi is of minimal degree, then the ring endomorphism of A is lifted injectively to endomorphism E to the n, if n is bigger than or equal to 2. And such thing has never happened for usual abelian varieties. So that if two abelian varieties are isogenous, endomorphism ring has no inclusive relation at all. But this case, because of class number 1, we can prove this. And once Franz Old told me that any talk should contain at least one proof, so that I'd like to prove this, since this is very easy. So the proof of reactability of endomorphism. This is really an easy exercise. We fix a supersingular abelian variety and assume that n is dimension is bigger than or equal to 2. Then module of endomorphism from E to the n to A is obviously the right endomorphism En module. And class number 1 means that this right module is principal, so that generated by some elements. Or in other words, this is free module over endomorphism E to the n. So that this is written as phi 0 and E to the n. On the other hand, if you take any alpha inside endomorphism, then alpha phi 0 is also an element of home E n to A. But we noticed that this is phi 0 mn, so that there exists certain beta in MNO such that phi alpha 0 is alpha 0 beta. So this diagram, if there exists alpha, then we can lift it to the beta. So you might ask, does it help? But actually, it helps a lot. So if phi 0 is written very explicitly, then usually we can describe endomorphism A inside the matrix algebra MNO. For example, when n is 2, we can really write down endomorphism of A concretely. So for simplicity, I assume that we take maximal order O such that the pi O contains pi, where the pi square is minus p. Of course, there exists always such maximal order. And then supersingular abelian variety, abelian surface is expressed by E square over iota alpha p, where iota is some embedding of alpha p, finite group scheme alpha p to the alpha p square. And this T is a sort of tangent. And A is divided into 3 cases according to this tangent. So that if T belongs to the finite group of all, p square order or infinity, then the A is congruent to E2, isomorphic to E2. And this is due to Franz Old. And this is well-known result in 1970s. And if T is not in FP force, then endomorphism is something like this. And it is somewhere intermediate, then endomorphism is something like this. So that this endomorphism is smallest, and this is a little smaller, and then this is biggest. And this is very easy result. Then, so I'd like to talk something like this for the polarizations. This is endomorphism, but I'd like to talk on polarization. So I start from classical results of Turing, and maybe you know very well about this. But if we denote by HP the class number of maximal order O of D, then and the TP the type number of D. Type number of D means that the number of isomorphism classes of maximal orders of D. Then in this case, we have this inequality. And Turing proves that the supersingularity curves are all isogenius of algebraically closed field always. And number of supersingularity curves up to isomorphism classes over algebraically closed fields is equal to HP. And any supersingularity curve has a model over AP square. In other words, J invariant always belongs to AP square. And the number of E which has a model over AP is equal to 2TP minus HP. And actually, all these numbers are explicitly written down. For example, class number is something like this, or here minus p over minus 1 over p, something like this is a residue, quadratic residue symbol, and h minus p is a class number of primitive quadratic forms of discriminant minus p or minus 4p. And one more interesting thing is that by this formula, we can see that this number HP is equal to the dimension of the weight 2 elliptic cusp forms belonging to gamma 0p plus 1. Plus 1 part is Eisenstein part, actually, but we can have such things. And this is a part of Aguilar-Jacques-Lange's correspondence between algebraic modular forms on D cross and new forms. Generally, the weight should be bigger, so that not only weight 2, but weight higher. We have some such result. Now, my aim is to generalize all these, and we can generalize all these in some way. But maybe about endomorphism of E, I can give a little more remark. So when E is defined over Fp, then endomorphism E can be completely explicitly written down by the following ring. So there are many maximal orders. So we need certain parameter for that. And then here parameter is prime number Q. And this OQR and O prime Q R prime, which is defined only when P is congruent 3 module 4, are both maximal orders. And endomorphism E, when E is defined over FP, are all written by these maximal orders. So for example, yesterday, Professor Eisenträger talked about endomorphism of E, and so he maybe her problem is to determine endomorphism of E starting from empty curves and so on. So my result is just we can list up all endomorphism rings by these modules. So for example, for me, if you ask which kind of empty curve is given behind that, I don't know. But anyways, all the list is given here. So I hope that this might be able to used in some cryptography theory. I don't know, but now we talk about general case. I mean, general dimensional case. So I switch here. So this is just preface in a sense, and then we switch to the general case. So to define the general case, first of all, the supersingular abelian varieties, there are a lot of supersingular abelian varieties, so that we cannot count such abelian varieties. But on the other hand, superspecial abelian variety is unique, so that there's no meaning to count that. So as counting object, polarization is a good candidate. So polarization is counted by quaternion hermitian lattices or quaternion hermitian matrices. So quaternion hermitian matrix is, as usual, defined as a H equal to the H transpose bar. And this is some connection with polarization. So we assume that n is bigger than or equal to 2. And we define the divisor x on e to the n. And n-fold self-intersection of x is very easily calculated, so that we can see that the mapping from en to the en dual, or pick en 0, is very easy to be isomorphism. So the phi x, here phi x is defined like this. Y is an element in a point in e to the n, and the class means a linear equivalence class, and xy is a translation of divisor x by y. And this morphism gives the isomorphism. And so this is a principal polarization. And any polarization of e to the n is identified with the endomorphism or quaternion hermitian matrix by this mapping. So lambda is actually the mapping from en to the en to the t, so that if we pull back by phi x, then it is contained in this. And this is for super special abelian varieties, but for any super singular abelian variety, we can do the same thing, so that we take the same phi x, and by taking the isogen here, then any polarization of lambda of A can be pulled back to the, again, Hermitian matrix over O. So any theory of polarized supersingular abelian variety should be explained by arithmetic theory of Hermitian matrices. That's my belief. So I'll give a lot of examples of this belief. So to define such thing, MND is too big object, or GLND is too big, and to control polarization or quaternion hermitian lattices, we need a kind of unitary group. And that unitary group is defined as a quaternion hermitian group. G is something like this. G star is transpose bar. The G is element in M and D, and NG is some element in rational number field, positive element. And this is actually the group of similitudes of quaternion Hermitian metric on Dn defined by this. So this is unique positive definite quaternion Hermitian metric on D to n. And this element of G is a similitude of this mapping, that is inner product of Gx and Gy is Ng times x and y. And also we need a local thing, so that for any prime, we define GQ by this, so that we change D to the local objects and Ng to the QQ cross. Here Q sub Q is a Q-adic number field. By the way, if you change D to the tensor, D tensor C, then we can see that G1C, where Ng is 1, this is isomorphic to usual symplectic group of size 2n. So this is somehow closely related to Ziegler modular forms. So in Ahira's case, it is related to the elliptic modular forms, but in our case, it should be related to Ziegler modular forms. Now we talk about quaternion Hermitian matrices, but actually it is better to treat this as a lattice language. So we say that lattice L inside D to the n, that is D to the n is a vector space of for n dimensional over Q. So the lattice is defined as a G module of rank for n, and this is called left O lattice if OL is inside L. So that this is a left O module. So left O module lattice L is called left O lattice. And when n is bigger than or equal to 2, again, class number 1 property means that any left O module is left O free. So this means that if we take left O module Li, then there exists certain Hi in this invertible element, and Li is written as On to the Hi. Here it is just G, L, and D, not G. And so by using this Hi is of course not unique, but this is essentially unique in a sense. And if we consider Hi to the Hi, small hi cross Hi star, then we have, this is a positive definite quaternion Hermitian matrix. So we say that L1 and L2 are in the same class if there exists an element in the similitude group that L2 is L1G. And L1 and L2 are in the same genus if there exists GQ, such that L2Q, L1Q, GQ for any Q, where LQ is a completion of L, Q-adic completion. And the matrix interpretation of this is as follows. Since this group G contains certain constants, so that to exclude such possibilities, and we assume that these lattices span the same two-sided ideal over O by this. Then in that case, if we put this and assume that these two-sided ideals are the same, then L1 and L2 belong to the same class if and only if F2 is epsilon H1 epsilon star, for epsilon is GL and O. And in the same genus if and only if these are locally true. So that, for example, in my language, H1, H2 are polarization geometrically. And what is epsilon? Epsilon is just an automorphism of e to the n. So the H2 equal epsilon H1 epsilon star means that the polarization H1 and H2 are isomorphic in the usual sense of abelian varieties. So this fits very well to the general picture. Now we'd like to explain general of maximal lattices, which is important also geometrically. So genus is, as I explained, this genus is determined by collection of local objects. So the genus means that the two lattices are all locally equivalent at any prime. So it is defined, a genus is defined by the local collection of the local lattices. And there are two important lattices called lattice of maximal lattices. And maximal means that if norms are the same, then and there's an inclusion duration, then M is L. So this is the definition of maximality. And there are two important, there are exactly two genera of left or maximal or lattices. So that we describe them by local quaternion Hermitian matrices belonging to that. One is called principal genus. So that is a genus represented locally, but unit matrix of size n. So this is locally, so the globally, of course, it's different, completely different, but locally represented by this. And also globally, it is represented by O to the n, but the genus contains a lot of other lattices, so the O to the n is just a local representative in a sense. So to write down all the representative of lattices is usually very hard. And there is another lattice. It is called non-principal genus. Actually, there's no definite name for this, but there are only two lattices. So, and this is principal genus is a common name. So that I usually call this non-principal genus. And this genus represented locally by 1n at any prime, which is not equal to p, and at p defined like this. Now, these two genera plays an important role in geometry. So the first application is principal polarization of superspecial e to the n. So the number of classes in the genus G is called the class number. This is usually very complicated, difficult object. Even in the case n is 1, then this is not so easy object. But anyway, we have a very abstract result on this. So the number of isomorphism classes of principal polarizations of e to the n, where e is supersingular, is equal to the class number of principal genus. So the superspecial abelian variety is unique, but the polarization is not unique. So that instead of isomorphism classes of E, we take principal polarizations. So if you consider the case n is 1, then in that case, class number is equal to the number of isomorphism classes of E. But it is changed for general setting to the number of principal polarization. When n is 1, principal polarization is unique, so that there's no point to count that. But in this case, we can count that, and this is not 1 at all. So explicit numbers of principal genus is known when n is 2. I'll show you later. And when n is 3, it is also known by Hashimoto. It is more complicated, but I don't write it down today. But a part of class number, to calculate class number, we need a lot of local masses or global masses. And essentially, class number is a summation of certain masses or related with the element, some element G inside the group G. So for example, if we consider the one unit, unit matrix, then the mass for that unit element is given like this. And so this part can be calculated generally. So here n is general. So the lambda I is principal polarization. So that we sum up this kind of mass, then that is given by this formula, where B2 2k is a Bernoulli number of degree 2k. Bernoulli number is generally might be minus, so that we put here the absolute value. So this is first result. So this is an example of number of principal polarization. So that if you take a two-dimensional superspecial abelian variety, then number of principal polarization of E2 is given by this. This is class number formula. And the first part of this is nothing but 2 times mass I explained of 1. So the contribution to this is coming from plus minus 1. So that this is twice of mass I explained before. Now, then I told you that there are 2 important genera. So there's okay, sorry. Yeah, I talk about Hecke operators, isogeny or Giga class forms. So that if you fix a genus and L1 to Ln are representative classes, and I denote by gamma I automorphism of Li. Automorphism of Li means element of stabilizer of Li inside G, quaternion hermitian group G. Then the Hecke operator is H cross H matrix of rational numbers, such that ij components defined to be the cardinality of this set. So this is somehow the isogeny from one polarization to another polarization. So when G is principal genus, then this is essentially the number of isogenies of degree n between corresponding principally polarized abelian variety. Now, for example, when G is non-principal genus and n is 2, then Hecke operator here is equal to the Hecke operator of paramodular class form of weight 3 of level P up to trivial part. When the elliptic modular case, there's a plus 1, and that plus 1 comes from something. But here also that plus 1 part remains. But anyway, essentially this is a dimension of paramodular class forms. Class number is dimension of paramodular class forms, and also the Hecke operators are the same. So this is analogy of the classical Ahilad theorem, and this is conjectured by me in 1984, including higher weights analog, and proved very recently by Van Hoften, and independently by Weissauer-Resner. And Hoften's proof is geometrical, and Weissauer-Resner proof is something different. And also we can ask the same question to the principal genus and the other genus. And actually, I have 3 different kind of conjectures of this kind of Lagrange type correspondence. But other cases very, very complicated. So the non-principal genus case is very simple, but other case is very complicated, and it has not been yet proved. But I don't talk about that. Now we switch to the Mujirai problem. So next we consider the Mujirai locus of principally polarized supersingular abelian varieties. So I already told you that the supersingular abelian surface A is given by E square over iota alpha P. And iota alpha P is determined by the tangent T. But tangent T moves around any element. And so, for example, T can be transcendental. So the general abelian varieties, supersingular abelian varieties has a certain moduli, so that it is not discrete. When n is 1, supersingular epic curve, number of supersingular epic curve is finite, so the supersingular locus of supersingular epic curve is just a discrete set. But when n is bigger than or equal to 2, then there exists a locus and there exists a dimension. So that in the coarse moduli or AN1, we consider the orbit of a supersingular A. Then the following theorem is due to Kessler-Oort, Ekdal-Oort, and Lie-Oort. So first of all, the locus Sn1 is connected. So I think this is essentially due to the Ekdal, and but not irreducible in general. For example, when n is 2, S21 is highly singular, and all the connected components are birational to P1, but not isomorphic P1. But and every irreducible component has dimension of this. This is for a function. For example, when n is 2, then this is 1, so that it is supersingular locus is one-dimensional. Now, since there are finitely many irreducible components, number of irreducible components can be counted, and it is equal to the class number of principal genus when n is odd, and class number of non-principal genus when n is even. Here appears non-principal genus. Again, the explicit formula for the non-principal genus is known when n is 2. I don't give a exact values of this, but anyway, such thing happens. So there are two objects: polarization of supersingular superspecial elliptic curves and the moduli locus of abelian varieties. So those two are different objects, but both are controlled by certain genus or polarization. So that's a bit mysterious things, but maybe in the end of my talk, I can talk something about that. Now then, we talk about class number problem. Next, I'd like to talk about type number. So in the classical case, type number has some relation with field of definition. In this case, if we fix a genus and write L1 and H representatives of classes, then we define a right order Ri of Li defined by this. This is right order. And this right order is always maximal order. But since class number is 1, so all maximal orders are isomorphic. So the Ri are all isomorphic to MNO. So in this sense, type number has no meaning. So we need some different notion here. So we generalize the notion of type number to this case in some different way. So we count G conjugacy classes. G is a quaternion hermitian group. We count G conjugacy classes in R1 to RH. And even if Ri is concurrent to MNO, if you take G conjugacy, then these might not be conjugate with each other. And this number of G conjugacy classes I call G type number. And this G type number is very good for our description of field of definitions. So the first result is the case of principal polarizations. So every principal polarization of lambda on En is defined by P scale. This is almost trivial. But the number of isomorphic classes of lambda defined over P is equal to this. Defined over Fp means that it has a model over Fp. But in any way, this is equal to 2 times T type number of G principal minus H G principal. This is exactly the same as in the case of classical Doring's result. Now, this is a theory about polarization of En. But in parallel setting, we can show the similar thing to the irreducible components. So number of irreducible components in Sn1 defined over Fp is equal to this or this when n is even or odd. So this is also very close to the Doring's classical result. So somehow we generalize everything, but I'll show you the explicit result here. When n is 2, G-type number is calculated. G-type number is much more complicated than the class number itself. Here, G2 chi is a Bernoulli number, generalized Bernoulli number with respect to chi, where chi is a quadratic character associated with q square root p. And this h something is class number of q square root minus p or minus 2p or minus 3p. And by seeing this, we can show that these two numbers are positive. So that there exists always a irreducible component defined over Fp. And by using the result on the two surface case, we can show generally that there always exists a irreducible component defined over P for any dimension n. So there exists irreducible component. Oh, sorry. Defined over P for any n. So that my proof is by using this, but later Chafu, you prove this in more direct geometrical way. So now since this is a cryptography conference, so that I also insert some result on the maximal curves. So I can show you by the sort of same techniques the existence of maximal curves of genus 3. So the Bay bound is, as you know, like this. So for every odd prime P, there exists a smooth project curve C of genus 3 defined over P such that the Jacobian is arithmetic over F squared to the superspecial E3 to the lambda. And in this case, we also have that number of Fp square rational point is 1 plus P square plus 6P, which is Bayes maximum. So that this is maximal curve. Now the proof is a bit more difficult. So the genus 3 case, every abelian variety is a generalized Jacobian, Jacobian of generalized curve. And it becomes a Jacobian of curve if and only polarization is indecomposable. But that does not help so much in a sense. That is, the real problem comes from the failure of Torell theorem over the field definition. So I think yesterday talk, Professor Seisling talked something about this, and we must cover a quadratic extension of this. And I heard about this by Sales letter in 1983, and he pointed out to me the difficulty about this. And so the proof is, the point of the proof is that not only to show the indecomposable existence of indecomposable lattice, but the point is to show that it is isomorphic to principally polarized abelian variety over Fp, which is isomorphic over Fp square. And this is a kind of descent condition, so that we can use Bayes descent criterion for the field of definition, and that field criterion can be interpreted as a certain existence of elements of endomorphism of lattices, and we can show by the complicated calculation that such elements really exist. In other words, we can show that the element mass formula of such element is positive. So that's my proof. So this is just existence theorem. So that I'm not talking anything about the explicit shape of C. So that, for example, if you want to say something about this, for example, if you take x force plus y force is z force, then it is supersingular when P is 3 modulo 4. But point here is that for every odd prime P, so that if you take a explicit curve, then if you calculate the Hasse-Witt matrix of that, then usually you can have a result that it sometimes become a supersingular and sometimes not. And sometimes usually means that the P belongs to the certain arithmetic progression. But if you gather arithmetic progression, then you cannot get all P. So this is something different. This is existence theorem, but very powerful. Okay. Then I explain something about the mass formula. I mean, how to calculate class number and so on. So in the easiest case, I'd like to explain how to calculate class number. So as I told you, if you take a representative L1 to LH, gamma I is finite group. This is finite group. This is a kind of isomorphism of polarization. And the number H, here 1 to H, number of H is expressed like this. This is just a stupid equality. This is just 1, so that you sum up 1 up to H, of course you can get H. So that this is trivial. So that you might think this is stupid. But we can decompose this into several parts. So that for fixed polynomial, okay, we can give a kind of trace formula to calculate this. So that this is a part of gamma I. And f can be taken as a characteristic polynomial of gamma. There are many f, but only finitely many f, because this is just a finite dimensional algebra. And then this Hg is a sum of these masses depending on f. So the trace formula is a way to calculate this. So to calculate the class number does not just mean to calculate class number, but to calculate all these masses, so that it gives you the information that how many gamma I contain some fixed elements. For example, if x is x squared plus 1 to scale, then this formula means that how many elements, which is x squared is minus 1, is contained in gamma I. And so this way of calculation gives you more information. And if you want to determine gamma I itself, then this formula is not enough. Because in a sense, this formula is a formula of traces of gamma I associated with permutation representation. And to determine gamma I, we must give a permutation representation decomposition. And to do that, this is not enough. And to do so, we a little bit generalize this, and we put here the generators. I mean, gamma 1 to gamma R and gamma I to the R, and then we can give a same sort of mass. And if we calculate all these, then we can calculate all gamma I. Of course, such calculation is very hard, but sometimes we can do that. So I'd like to explain automorphism groups. So when in the composable polarization of superspecial surface, then this case, this is Jacobian of C. So essentially the automorphism is an automorphism of C by Torres theorem. So this is easy. And this is done by using Igusa standard form in the paper with Kassler and Oud. But for example, the automorphism group of non-principal genus is very hard. Then this non-principal genus automorphism group is automorphism of a certain family to giving by components. And in that case, we can give all these things. And also when A is a supersingular surface, which is not E2, then in that case also we can give a concrete automorphism group. So again, we must divide cases. T is not included in or this. And by using this kind of automorphism groups and certain kind of different type of mass formula, we can give a number of principal polarization of supersingular surface, which is not equal to E square. So if we denote HA, the number of isomorphic classes of principal polarization of A, then it is given as follows, very, very concrete. So in this case, isomorphism classes of principal polarization is equivalence of matrices up to automorphism of A. And the automorphism of A is not GL2O, a little bit smaller than that. So this is not included in the general theory of G. And this is some sort of a different algebra. But anyway, this is not so difficult algebra, and we can solve this. And so we can do this. Now, finally, I'd like to explain Mujirai problem. So, as I told you, supersingular locus is controlled by certain genus, and superspecial abelian varieties controlled by another genus. And superspecial abelian varieties on the some irreducible component of the locus. So we can ask which kind of superspecial polarized abelian variety should on which component and so on, which component includes superspecial epic curve, and how we can control that. And so that this is a little bit complicated to explain, and I don't want to introduce other group here, so that we just say that we can define a number, and we have families of fixed a numbers in each irreducible component, and so in this case a number is 1 or 2 or 3, and those families correspond to certain adelic double cosets. So adelic double coset is something like a principal genus or non-principal genus. Anyway, this is a stabilizer of lattices in adelic sense. And those adelic stabilizers are all parahoric subgroups. And configuration of these families are controlled by the adelic double cosets. For example, their intersection or inclusion relation are all controlled by the fact that two corresponding double cosets has non-empty intersection. So the present problem for me is to do the higher dimensional analog of this. And so I hope that I can do that in future. So this is the end of my talk. Thank you very much.
Thank you very much for this very interesting talk. So let's give a round of applause. All right, so we are a bit behind the schedule, but are there any questions? So please, Valentine.
Yes, thank you very much for the very interesting talk. I had a question about the arithmetic part of the theory that you were explaining at the beginning, because you mentioned these maximal lattices, and I was just wondering what is known about non-maximal lattices, and do they have a geometric interpretation as well that is interesting?
Yes, non-maximal lattice appears actually in the description of a number 2 families of the dimension 3 abelian varieties. So as you know, there are flag type constants. There are 3 abelian varieties, and in the middle, somehow it corresponds to the non-maximal lattice, non-principal genus, not principal genus, and not non-principal genus. And there appears some another lattice. Actually, it is a dual of non-principal genus, but this is not maximal. So some such thing happens. So if you consider the higher dimensional cases, there are a lot of other lattices appears, I believe. And this is somehow related with the Heck operator of the SLN and so on. So that seems very interesting.
Thanks. Yes. So that was, I guess, my question. How can we interpret those as Heck operators? But you're saying that is also known in some cases.
Yes. So I explained here something like this, but here actually Heck operators above SL and SL3O appears, and in the flag type constants, each principal polarization belongs to certain Heck operator. And dimensional 3 case, it is a very lucky situation that there appears only one Heck operator, essentially, in that sense. And when you consider the abelian 4-fold, then maybe there are 2 Heck operators, Heck double cosets appear there with respect to SL and O, and the higher a lot more. So the things becomes much complicated. But if we consider all the theory for each double coset, maybe we can control that, I believe.
Thank you.
All right, and then a question by Samuele.
Yes, my question is a bit naive. I hope what we will see. So almost at the beginning of your talk, you gave some results about comparison of equiparators for single modular forms in the paramodular and non-paramodular case. If I remember correctly, there is you were saying that some non-paramodular form is related to some paramodular form. So I wanted to ask if that has some relation or has some effect or implication towards the paramodular conjecture right away.
Yeah. It's very different because parametric conjecture, you mean parametric conjecture of abelian variety?
Yes, for abelian surfaces.
Yeah. So the parametric conjecture of abelian variety is weight 2.
Yes.
And mine does not contain weight 2. So weight 2 is very special. It is something like a weight 1 for the elliptic modular case. And that's very strange object. So for example, dimension of weight 2 for the Giga modular case is not known at all. Of course, if you fix a group to the very special, of course, we can calculate, but for general setting, it is not known. So, and also in this setting of the Jacquelin's correspondence, the weight should be bigger than or equal to 3. Weight 2 does not appear there. So I cannot say anything about it. I have no feeling.